Okay, we're going to look at some examples of constrained optimization problems. So we're looking to find a vector in R3 with length 5. So we have a constraint whose components have the largest possible sum. So we want to maximize something here. So that would be how we would know when we read this that we have constrained and then optimization problem. So sometimes there are different ways you can do these problems, but in general, if you have a lot of variables, Lagrange multipliers is a pretty good strategy for handling these constrained optimization problems. All right, so when we think about Lagrange multipliers, we have two functions that we need to write down. One of them is the objective function, and that's what we want to maximize or minimize. Objective function. All right, so we have to read this problem, and sometimes they hand you a function that you want to maximize or minimize, or sometimes you have to write that function down. All right, so we want to find a vector in R3. I don't have any variables listed here, so I'm going to write down some variables for that. So this is ultimately what I want to find, a vector with 3 components. So each of those components is an unknown. So what I want to find, maybe I'll write that like this, a vector. And then each of the components, I could call them V1, V2, V3. Subscripts are not always fun to work with, so I'm just going to use some different letters here. I could use A, B, C, or maybe more natural to just use X, Y, Z here. Remember what we're coming up with here is a vector. So I want a vector in R3 with length 5 and whose components have the largest possible sum. All right, so here are my components. My objective function is what I want to maximize or minimize, and so that's what we're describing right here. So I need to write down a function that describes largest possible sum of components of these vectors. All right, so my function, I could name it S for sum, but I'm just going to use the letters that are in the Lagrange theorem here. F is what it calls the objective function. So my objective function, it's a function of 3 variables, and it's just the sum of the components. Components have the largest possible sum. Okay, so this is the function that I want to maximize. And then the other part of a constrained optimization problem is identifying what is the constraint. So there's some kind of restriction, and you need to express that as an equation, also involving your variables here. So I need this vector to have length 5. So the constraint has to do with the magnitude of a vector. So the magnitude of this vector would be square root of x squared plus y squared plus z squared. I want that magnitude to be 5. So that's the restriction, length 5. When we think about Lagrange multipliers, though, it talks about a function in our theorem. It calls that function g of x, y, z, our constraint function. And we need that function equal to 0. So although this is my constraint, as it's described here in the problem, when we're going to use Lagrange multipliers, I need to do a little bit of algebra here to rewrite this so that I can think of this as a function of 3 variables equal to 0, so a level surface of a function of 3 variables. So one way I could do that is just by subtracting 5 from both sides here. But remember, in Lagrange multipliers, you're going to have to take some derivatives. And if you think about taking derivatives of this, that starts to become a little bit complicated. So I'm actually going to do a little bit of algebra first, and then rewrite my constraint function based on that step of algebra I do first. So really all I'm going to do is simplify this equation. As long as what you're doing is legal algebra that maintains the equality in your equation, it's perfectly fine to do that. So I'm going to square both sides of this. So that is something you can do to both sides of the equation and maintain equality. And so now I get x squared plus y squared plus z squared equals 25, which is going to be much easier to take derivatives of. All right, but still, I need to make sure that I've got a function of 3 variables equal to 0. So my constraint function, I'm just going to subtract 25 from both sides of this. So my constraint function will be g of x, y, z equals x squared plus y squared plus z squared minus 25. And I need that constraint equal to 0. Okay, so when you're doing a Lagrange multipliers problem, it's important that you identify whatever it is you want to maximize or minimize. Be clear that that's your objective function. And then what is the restriction or the constraint? And you need that as a function of 3 variables set equal to 0. All right, and then what Lagrange's theorem says is that if this objective function has an extremum subject to this constraint, it occurs at a set of values that satisfy a system of equations. So I'm going to write the system down over here as it is stated in the theorem. But in terms of the mechanics of solving it, sometimes I don't always write that step out. So sometimes I go right to the next step. So for this first example, though, I'm going to write down exactly what the theorem says. It says that if this objective function has an extremum that does satisfy this constraint, it satisfies the system of equations given by gradient of f equals lambda times gradient of g. Remember, lambda is just a scalar multiple here, and g of x, y, z, or whatever the variables are, equal to 0. So we need to solve this system of equations. So I'm going to write down a step over here, but in most of the problems after this, I will actually skip writing this step out and go right to the algebra of solving that system of equations. Okay, so the gradient vector for this problem, gradient of f, I'm going to have, I'll just rewrite this here for our particular f function. Partial derivative of f with respect to x is 1. And partial derivative of y, f with respect to y is also 1. And partial derivative of f with respect to z is 1. This is about the simplest possible example I could do of this problem. Is equal to lambda, that's an unknown scalar, times the gradient of g. So I'm going to take the gradient of this function. So partial derivative of g with respect to x will be 2x. Partial derivative of g with respect to y will be 2y. And partial derivative of g with respect to z will be 2z. And then the constraint equals to 0 is the other equation in our system. A lot of times students will get lost in the algebra, and it's often because they've forgotten that constraint equal to 0 as one of the equations. I'm going to actually go back to a previous step. I can write down this equation equal to 0, but when I do the algebra, I will probably want to add 25 back to both sides for that. Okay, so I'm going to be solving this system of equations to do my work here. When we do that, when we've got this vector equation, I often go right to what I'm going to write over here, and that is that the components are going to have to be equal. So the I component of this vector is going to have to be equal to the I component of this vector, remembering that I've got a lambda to distribute through on all of those components there. So the system that I'm actually going to end up solving is going to be 1 equals lambda times 2x. And then 1 equals lambda times 2y. And 1 equals lambda times 2z. And then this is the fourth equation. Notice I've got 3 equations here with 4 unknowns. So that's not enough equations for the number of unknowns. A lot of times students will write down that much and then get kind of stuck. So remember, the constraint equal to 0, or you can rearrange that doing some algebra, is that other equation you need. All right, so this is the system that we're going to be solving. And a lot of times, instead of writing this step out, I will just go right to here. So these are my partial derivatives with respect to x of both my objective function and my constraint. Partial derivatives with respect to y of objective function and constraint. Partial derivatives with respect to z of objective function and constraint, with lambda times all those components for the constraint. So a lot of times I'll go right to this system and solve this. one of the comments that I mentioned when we first talked about the theorem is that one of the textbooks I used to use said something about these systems of equations often require ingenuity. So the algebra is different than you might have done before. So just think about algebra, make sure you're doing things to equations that preserve the equality, that you're not moving things around in ways that are not correct algebra. But you all know algebra. Just leverage those algebra skills and think about this. One of the things that you do have to be careful about sometimes is dividing through by variables. And so you need to think about if the variable could be 0, you really should avoid dividing by that. It's kind of tempting here perhaps to divide through by something here, which you could do, but you have to be careful to ensure that none of the variables could be 0. In this particular problem, if we look at these first 3 equations, you can see that none of lambda or x or y or z, none of those variables could be 0, because if any of those variables would be 0, then these constants on the other side of the equation would have to be 0. Right? If lambda were 0, it would force all these equations to be 0 on this side. If x were 0, it would force this one to be 0. So in this particular problem, none of x, y, or z will be 0, so we can feel free to divide through by them. All right, so the thing I might notice when I look at all of these equations is that I've got equations relating x and lambda, y and lambda, z and lambda, and then this equation relating x, y, and z. So I might choose to solve these first 3 equations for x, for y, and z, get an expression in terms of lambda, and then substitute in here. Any algebra you do that's correct algebra should get you to the right answer. It's just a matter of making sure that you do that kind of efficiently and don't make any algebra errors. Okay, so on this first equation, if I solve for x, I will get 1 over 2 lambda. And in the second equation, the same thing. And in the third equation, the same thing. And then if I substitute those into my constraint, then I'll be able to solve for lambda. And then once I know lambda, I can figure out my x, y, and z values. All right, so if I substitute those into my constraint, I'll have x squared. So I'll have this whole thing, the quantity squared. I'm going to go ahead and square that. 1 squared is 1, 2 lambda squared. The quantity squared will be 4 lambda squared. And then y, same thing here. And then do whatever algebra you want to do to solve this. I might notice that I have 3 fractions here all with a common denominator, and write that as 3 over 4 lambda squared is 25. Ultimately, I really am interested in solving for x, y, z. If I happen to find lambda along the way, then that's fine, but I don't actually need lambda to help me solve this problem. Lambda is just a scalar. It talks about these 2 vectors being parallel here. So in this case, I will find lambda. So maybe cross multiply and divide. So if I multiply both sides by 4 lambda squared and then divide by 100, I get 3 over 100 is lambda squared. Or lambda is plus or minus, be careful about that, square root of 3 over 10. Okay, so I actually have 2 lambda values here, so it's important to notice that. And then depending on which lambda I have a different set of x, y, z. And then we need to determine which of those answers, if either, actually answer the question here that we were after. All right, so using these values here to find our x, y, z values, so that we have our vectors here, when lambda is positive square root of 3 over 10, if I simplify this, I will get x equals 1 over 2 times square root of 3 over 10. Or if I simplify that, I'll have x equals positive 5 over square root 3. And then same for y, and same for z. I put these into components of a vector, because remember, that's what we were after in answering this particular question. So this is one set of x, y, z values that occur when I get lambda equals the positive square root. And then when I use the negative square root, I get a separate set of components. So negative square root of 3 over 10, when I put that in here for x, and then for y and for z, it will get negative 5 over square root 3 for all of these components. Okay, so sometimes students just get an answer and stop there and maybe put a box around it and stop there and go on to the next problem. But the important thing about these optimization problems is to understand that there are really several possibilities that could happen when you get these answers. One is that you get some values that maximize the function, the objective function, and other values that minimize the objective function, and you may not be looking for both. Here I'm looking for the largest possible sum, so I'm looking to maximize my objective function. It could also be that you get some points here that are actually like saddle points, where you have function max or function min values on either side of that, or you don't actually have a max or min value, but the function gets larger or smaller on either side of that point. So you want to think about these values and make sure that they actually do maximize or minimize or whatever you're after your function here. All right, so if I look at these two and think about these as my values for x, y, and z in my objective function, you should be able to look at those and think about that one of those gives a higher output value than the other. Right? When I put in these positive values for x, y, z, I'll get a positive output for this objective function. And when I put in these negative values, I'll get a negative output for this objective function. So what we're after here is a largest possible sum. A negative answer is not going to give me a largest possible sum. So this is my possible candidate for a largest possible sum. This one perhaps might minimize the function, the objective function, but certainly doesn't give us a largest possible sum here. The other question might be, are there other values that do give larger possible sums? Is this like a saddle point? And so one way to think about that too might be just to find another vector with length 5. So it should be easy for you to write down lots of vectors of length 5. And think about those other vectors of length 5, what do they give for that output function? So for example, if I think about probably the easiest vector you can think of length 5, 5, 0, 0, and you think about that into your objective function, the sum of the components here, f of x, y, z for this gives you 5, whereas f of x, y, z for this vector gives you 15 over square root of 3, which simplifies to be 5 over square root of 3. So this gives a larger output than this other value. And you can try others as well to ensure that it's not a saddle point, that what you have here doesn't give a saddle point. But in this case, this gives a smaller output value. F of 5, 0, 0 is only 5, where f of this combination of values gives you a larger value. So this one maximizes the function. But the point here being that don't just get some answers and assume that whatever answers you've gotten actually maximize the function, what you're after. You need to make sure that you think about that. It could be that one of your sets of values actually minimize the function. The other thing to think about sometimes that can help you with that is to think about the geometry of your constraint. So in this case, our constraint is a distance formula. We started off with a distance formula, but in here you can see we've got an equation of a sphere. So you can think about all of the points, x, y, z points, which would be the terminal points of this vector, on a sphere. You can think about that of all those points, there would be some that would have a maximum possible sum and some that would have a minimum possible sum. So this is the one that gives you your maximum possible sum of components, and this one gives you your minimum possible sum of components. These other points would just be somewhere in between. All right, so the point being, make sure you think through your answer, whether it really does maximize the objective function or possibly minimize the objective function where there is no maximum. we will look at some examples where that actually is the case, where there is no maximum or minimum. All right, we'll look at some more examples and some more videos.